We start now the first presentation that will be a shared presentation given by Erika Saretta from SUPSI and Xiang Ma from SINTEF in Norway. They are both part of the SuperPV project, and they will talk about digitalization and information management as drivers to support cost reduction of PV. Erika, Xiang, I don't know who starts first, but the floor is yours.
Yeah, I'm going to start. Thank you, Michael, for the introduction. I'm going to share my screen. Now you should be able to see my full screen, right?
Yes.
Okay, perfect. So good morning, everyone, and thank you for joining this webinar and to the organizers for this opportunity to present activities of SuperPV project. My name is Erika Saretta, and I am a researcher at SUPSI, Switzerland. I'm leading the work package of SuperPV project about PV integrated process and information management. And guess what? Today I'm going to talk about digitalization and information management as drivers to support PV cost reduction. I am happy also to present Dr. Xiang Ma from SINTEF, who is going to co-present today and provide more details and insights on digital tools and data mining tools for manufacturing. So just a few words about SUPSI, that is the University of Applied Sciences and Arts of Southern Switzerland. We are located in South Switzerland, exactly here. And we cover a wide range of activities in both education and research, and in particular, the Department of Architecture and Construction includes also the Institute for Applied Sustainability to the Built Environment, where my colleagues and I are mainly devoted on research activities on these 4 Ds. So decentralization of electricity production from photovoltaics, decarbonization in the built environment and mobility also, digitization in electricity management and construction, and finally, democratization of energy by way of involvement in real life. So if you want to investigate and know better our activities, please refer to our website. In particular, I work at the DIPV team with colleagues you can see here, and our mission regards applied R&D of systems and tools for supporting industries in the implementation of PV in the built environment. Moreover, we are devoted also to the validation, optimization, and testing of new BIPV concepts and products. And finally, we are involved in education, dissemination, and technological transfer. We are taking part to several Swiss projects and also in a couple of H2020 projects, and one of these is SuperPV. SuperPV is aiming for innovative PV system cost reduction and significant LCOE reduction by adopting, let's say, hybrid combination of technological innovation that you have also seen yesterday and data management tools along the PV value chain to accelerate large-scale deployment in Europe. These innovations regard PV modules innovations, power module level power electronics, and PV system integration and process innovation. And all these 3 innovations are aimed at reducing the LCOE. You can see here the expected LCOE reduction, and specifically about concerning the PV system integration and process innovation. The expected LCOE reduction is in the range from 12 to 18%, plus an additional reduction due to data management during manufacturing stage. And this is exactly the goal and the topic of work package 5. Indeed, we observed a fragmented process in the PV value chain that creates informative gaps among design, manufacturing, installation, and O&M stages. And these gaps involves also huge efforts extra time, repetitive work, risk of mistakes, information losses, and so on, that causes extra costs along the value chain. And for this reason, the goal of our activity is to adopt digital solutions and tools to ensure an integrated PV information management. We named it as PIM, and the goal is to reduce the costs and also extra costs related to PV projects implementation and the operation. Translated into real terms, this means for us the development of a digital platform for design, simulation, and operation, supporting the cost reduction of PV systems, but also the development of a tool for extending this PIM-based platform for the O&M through digital twin models. Maybe now you are asking, what is PIM? Let's say that PIM arises from BIM, that is the acronym for Building Information Management. This is a digital and collaborative approach based on building data sharing among different stakeholders and different stages of the building process. And this approach involves modeling not only the geometries, but also information associated with objects and geometries. And it has been demonstrated in the building process a dramatic reduction of time and efforts, mistakes, and extra costs, thanks to this approach. So we adapted and we tailored this approach to the PV industry by introducing also here a collaborative digital approach that we named PIM, or PV Information Management, for developing this integrated and interoperable PV process aimed at overcoming these informative gaps that I mentioned before for supporting the PV cost reduction. In SuperPV Project, we developed this PIM strategy that actually takes us three main work stages, which are the manufacturing, the design stage, and the O&M. And we envisioned digital sharing of data and information among these stages. So indeed, from manufacturing, PV module data can be used for design and simulation, as usually it is already done. Then when the PV plant is built, we will have the as-built model. But this as-built PIM model is not only geometrical model, but it also embedded information about PV components that are used. And this model with embedded information can be directly used in the O&M stage, and during the O&M stage, by monitoring the performances and the behavior of the PV plant, we can also provide feedback to the simulation model, so we can improve the simulation model thanks to real data and the real behavior of PV plant to improve the design of future PV plant, and so in this way reducing also costs of future PV plant. But also we can collect data about the real behavior of PV modules, and we can provide feedback to manufacturers on how to improve the PV modules to improve the efficiency and reduce also the costs. So in this way, the loop is closed, and as you can see here, the information can flow from one stage to another one, and also provide insights and more knowledge to improve the process and the different steps. So translated into real terms, the PIM has been implemented within SuperPV Project through a set of tools and software, and in particular, SINTEF, and particular Xiang, is developing the data mining tool for finding correlations among PV module properties and manufacturing steps that is going to affect the CapEx. We have also first prototype of a SuperPV tool for cost-driven design that allows reducing time in design, but also to create a model with this embedded information that can be used in the O&M stage, where we will have two digital twins, one for the product lifecycle management of PV modules, and the other one for the smart O&M, so for the smart management of PV plant that allows to reduce the OpEx. And finally, we have a data mining tool that is going to be developed for finding out the correlations between product performances, properties, and the event that appear or can appear in the infant stages. That is going to affect also, in this case, the CapEx, thanks to the feedback that will be provided to manufacturers. So now I can let the floor to Xiang Ma, who is going to explain a little bit more in details these two yellow boxes. And thank you for your attention. So Xiang, the floor is yours.
Yes. Thanks, Erika. Yes. Can you see my screen now?
Yes.
Yes. Good morning, everybody. I'm Xiang Ma. I'm working in SINTEF in Norway. And together with the partners in the SuperPV consortium, we are happy to share some of the case study using the digitalization tools for the manufacturing process. There are several typical failures in different stages of the wafer-based crystalline PV module when they start from the operation. The curve here is taken from one of the reports. Here it's a report from other people's work. They're typical problem due to the laminations here, and also some of the problem also could be the material used to seal the panel, like they use the EVA material here. Anything could happen and impact the PV module life. In this talk, I would like to focus on the scenario. One is the lamination. Lamination is a very important process in manufacturing the PV module, and maybe the most important one, because it's once you've done the lamination, all the process cannot be gone back. Before lamination, if some of the thing happen, like if you find some of the cracked cell, you can very easily to be replaced. But once you finish the lamination, everything is sealed, cannot be fixed. And also this lamination provides the panel durability. During the lamination, one of the critical process parameter is temperature. The temperature is just used to heat up the layer to melt the EVA material and etc. The low temperature could cause cross-link the EVA polymer and make the material, the panel actually to be easily to be oxidized and hydrolysis. And if the temperature is too high, it might weaken the interfacial adhesion and form the lot of bubbles could be created. So it's very critical to control the temperature. So also if you have some the bad thing happen, also can create some of the corrosion around the bus bar. So it's important to keep in mind that temperature control is important. The next slide is taken from the data collected during the manufacturing the process, and this the data provided the Solitech, the partner within the SuperPV consortium. And in the previous slide, it's a dual. This laminator can produce two panels in the same time, can laminate two panels in the same time. See here, we call the chamber 1 and chamber 2. The temperature, this is varies a long time, it's over one night, or over 1 day. And see there are a couple of the positions, collect the temperature data. You see the bottom, the plots, and somehow they are a little bit different. And top one, you can see the tank temperature. They are like also varied in some degree. It's important to analyze the variation. See the next slide we took from the plot the temperature curve in a very short period of time, like 40 minutes. And see here the two stages have a different temperature variation. So slightly like I would say it's 2 or 3 degrees difference. But how this is important is actually we have to combine with other the analysis, like using the results from the flash test results, and also possibly like analyze the electroluminescence image. You have to ask to identify some of the defects, and these defects could be caused by the lamination, the temperature variation in lamination. And second case we would like to present is the crack detection using the image processing technique. Here is the PV module, the image from the electroluminescence, the scanning, also provided by Solitech. And the panel see here is quite clean, almost nothing. So we should be happy with even we run the crack detection, we show nothing. But somehow, if you, in this case, if we can scan use the codes to process the one cell with the very obvious crack here, and the right hand side is in the black and the white, the background, see the crack is very obvious, but we have to label the crack and then as a reference. And the left hand side is from the EL scanning. We should be here. We acknowledge the original source code is from the pattern recognition lab developed at FAU in the university in Germany, and we adapt that code to suit our purpose. The slide show here is the result using the image processing to process the cell showed in the previous slides. And see here we have a region of the interest, and all this the big vertical, the black lines, the bus bar. And due to the low resolution, we cannot see the tiny the grades, but the obvious the crack is definitely is showing this the picture. And you can see that we run the several the technologies before filter, after filter, maybe not big difference. But if you run the equalization, you can see some of the details. But some of the tiny details, according to previous slides, the reference is they are not correct, and then you see here. And if we use a different algorithm, even we can look at further and identify some of the very tiny. Maybe they are the very I would say minor some of the defects, but it's not very easily to be detected by our eyes. And then we have the plots to show how close the image processing can match the reference the image, and we call it the receiver operating characteristic curve. And the curve is cover the whole area. See here, the down to the bottom, according to the false positive the ratio. If the curve is higher than others, that means they are close to the reference case. That means match the label defect. See here, the algorithm ECS 2.2 are doing the best. And this one is a purple curve. Sorry for this very tiny thing, the line. We should make thicker. Yes, and also we are still improve the codes and use the final to improve the source codes to process in the large scale of the module level. Before it's only the cell level. And then we can recommend use a workflow. See here we identify the two.
1 minute, Xiang, please.
Okay, I will be done in 1 minute. Like we identify the critical process step like soldering and lamination. They are crucial during the manufacturing step. And now we got the EL imaging before lamination and after lamination. And then we run the flash test to get all the performance data. And we try to link this processing and the performance and get create the analysis for the panel once in the operation the stage. That's all. Thank you very much.
Thanks, John. Very nice presentation. I think we're already running a bit behind time, so I would suggest that we kind of keep the Q&A in the chat room. So I think I already saw a question to Erika, and I would like also others to please ask questions, and please take the time also to answer these questions. I think yesterday some of the questions remained unanswered. I think that's a great opportunity to talk to many people that are interested. Okay, thanks again.